So good afternoon, everyone. My name is Ignacio Julian. I'm Technology Project Manager at CIRCE Technology Center, and I'm going to summarize the latest developments on the framework of microwave-assisted wind turbine blades recycling. But first, a few words about CIRCE. CIRCE is a technological center based in Spain, exactly in Zaragoza, in the northeast of the country, with more than 300 professionals and more than 30 PhDs, so doctors, working on research, development, and innovation in the fields that are highlighted below. So within all these fields of knowledge, we are focusing our research within Refresh in these three categories, so energy efficiency and decarbonization, recycling, and industrial technologies. So all of you know the challenge of wind turbine blades recycling. So despite having several options, most of them are currently landfill or incinerated. So the possibilities not to do so are the blades repurposing for low amounts of material. One can create urban furnitures, but most of the wind blades are then recycled either under mechanical conditions or under thermal and thermochemical treatments. So my colleagues who were presenting the mechanical methodologies carried out at GIS and also the thermal recycling through pyrolysis in GenCraft. So we are more focused in a particular case of thermal and thermochemical recycling, that is the solvolysis and pyrolysis. Both technologies evaluated at the same time under microwave-assisted heating. Why microwaves? Because microwaves are able to heat selectively the material that we want to pyrolyze or solvolyze, and decreasing the starting up and shutdown periods along the process. So as you can see here on the top left, the temperatures rise too high to reach a constant temperature for pyrolysis compared to conventional heating, but also the full depolymerization times for resins that are contained in the composites are drastically decreased by using microwave heating. As you can see, more than 5 times faster is the process. And the reason is that we can heat selectively the material that we want to process, being the surrounding atmosphere completely colder or much colder. So in this way, we can even control how the gas phase, the organic vapors that are generated through pyrolysis, we can control how they evolve, how they keep on reacting due to this temperature gradient between the sample and the environment. So as you may know, resins have very strong heat transfer limitation. So the heat transfer is very pure. And that's why large temperature gradients along the thermal medium limit the recycling process controllability. And furthermore, gas phase cracking in the hot reaction system atmosphere also limits the oil production distribution controllability. So the molecules that we're going to get out of these resins. Contrarily, microwave-assisted heating gives some advantages. As said, fast, selective, and volumetric heating that aim to control the pyrolysis process and the oil product distribution. Furthermore, we have realized that the apparent temperature of the process is significantly lower than under conventional heating, and that gives a better control on the mechanical properties of the resulting or reclaimed fibers, as well as of the oils. So to carry out the proof of concept of this technology, we count on two different reactor units, the microwave pyrolysis process unit and the microwave solvolysis unit. Both microwave cavities can hold tanks up to 1 liter capacity, and what we were evaluating are the process conditions, so temperature, residence time, and also flow rates, to get the maximum in terms of oil yields and productivities, as well as clean fibers. So as you can see there, by pyrolysis, we are able to separate fibers, but they become cooked unless we use a kind of a combustion step to remove these carbon deposits. While under solvolysis, we are getting clean fibers and oils. The quality of oils will be compared later. So under pyrolysis, we were processing both epoxy and polyester composite resins. And we found that the most impactful parameter in the process operation is the pyrolysis temperature. So if the temperature is too low, we cannot remove the resins. If the pyrolysis temperature is too high, we damage the fibers. They start to melt. Under polyester resin, we observe more or less the same, but in this case, the residence time was to be optimized because the time that vapors spent in the hot zone of the reactor has a big impact on the quality of the oils that can be obtained. Regarding the oils, the ones from epoxy can get up to 80% in weight of phenols, mainly P-cuminol or BPA, that are the chemical building blocks of the epoxy itself, so they can close the cycle towards the production of new epoxy resins. In the case of polyester, what we get is phthalate and phthalic acid derivatives that represent more than 70% in this case. But if we look at the atomic composition, carbon, hydrogen, oxygen, nitrogen, the composition of these oils would be also suitable as fuels, as precursors for fuels. If we go to solvolysis and we do the evaluation of both epoxy and polyester FRP composites, what we get is that the fibers are cleaned, more cleaner than those under pyrolysis, but they still have deposits, not of coke in this case, but of the catalytic salts that we use for enhancing the depolymerization of these resins. The composition of the oils is rather different and is strongly dependent on the solvolysis medium and catalyst that we are using, and the amount of oxygen in the atomic composition of the oils discourages its use as fuel, but also discourages use as a chemical building block. So comparing both pyrolysis and solvolysis, we have three categories for comparison. So the oils, the fibers, and the process itself. In case of pyrolysis, the oils have a relative high value as chemical building blocks. Phenols and phthalic derivatives products are obtained, and they can be used as additives for naphtha production, as said. Regarding fibers, they have typically low value, although better textural properties preservation with respect to the conventionally heated pyrolysis process due to the use of a lower apparent process temperatures, and the process itself is energy demanding due to the high temperature, roughly 400 to 500 degrees Celsius, but the separation, the isolation of the oils from the fibers is pretty easy. So if we want to recover clean fibers, we need a post step based on coke combustion. Regarding solvolysis, the potential value as building blocks for the oils strongly depends on the medium catalyst and operating conditions being typically lower than that of the products obtained under microwave-assisted pyrolysis. The fibers have relatively low value with no structural damage and cleanliness, but the length of the fiber is rather low because we need to pre-shred them to be fit on their stirred tank reactor type. The process is typically less energy demanding in terms of thermal processing, but the complexity of oil isolation and the materials demanding, so solvents, catalysts, post-processing agents, makes the process less attractive. So frequently asked questions that we normally get: which is the most appropriate technology among or between microwave pyrolysis and microwave solvolysis? Well, we did a techno-economic assessment of both technologies, considering the whole value chain, namely from the shredding and sorting and pro-processing through the thermochemical process and oil separation from fibers. And what we got is that both the OPEX and CAPEX of the microwave-assisted solvolysis is almost twice higher at this bench scale than those of microwave pyrolysis. The analysis, of course, excludes the cost-benefit assessment derived from the recycled product's quality and the potential selling price. But is this technology scalable? The answer is yes. We create the first of a kind microwave-assisted continuous pyrolysis process for the composites and also from polyolefins mixed waste that is able to process up to 30 kilograms per hour of shredded FRP waste with a nominal input power of microwaves of 9 kilowatts. And the output of the process are sorted and cleaned fibers together with pyrolysis oils. By evaluating the techno-economic analysis of this new pilot plant that has been already built and is under commissioning at CIRCE facilities, we got a 120 times normalized reduction of energy to run the process under continuous operation, plus 58 times OPEX reduction and just 5 times CAPEX increase with respect to these bench scale plants, to hold 1 liter capacity. So, conclusions and outlook. The microwave heating boosts the energy efficiency of wind turbine blades recycling down to 3 times lower consumption per kilogram of FRP treated. Enhances also process controllability, oil products distribution, and also the reclaimed fibers quality, keeping up to 80% of the original mechanical performance. Both pyrolysis and solvolysis technologies were experimentally assessed. Both may provide fibers and oils. And the techno-economic assessment reveals that the overall cost of pyrolysis is roughly 2 times lower than that of solvolysis. The quality of fibers are comparable between them, especially if we apply the post-combustion treatment to the fibers from pyrolysis, while the oils from pyrolysis are more interesting from the end-use point of view. And finally, a new pilot plant is being commissioned at CIRCE premises to assess the process scalability and energy efficiency of this kind of microwave-assisted pyrolysis solution. The nominal or maximum capacity of the plant will be 30 kilograms per hour and will be available for bench trials for potential investors. And that's all from my side. Thank you very much.